this be what I want it to be and to give a little bit better instructions, I would have to say find the first four non-zero terms and the general term of the Taylor polynomial. I need to give you a centering point. So I'm going to say at c equals 0, making this really one of those Maclaurin polynomials. So find the Taylor polynomial at c equals 0 for f of x equals e to the x. So if you need to, refer back to the basic construction techniques that we saw for these and see if you can do number 6. Just the first four non-zero terms. So I didn't give you a degree here, I just said first four terms, non-zero terms. Thing, the general term as well. So for your polynomial, the first term is going to be f of 0. F of 0 is just e to the 0. And e to the 0 is 1. So term number 1 in our polynomial would be 1. Of course, the nice thing about this is any derivative degree of this f of x is just going to be the same thing. So you might, if you wanted to, you could just put the nth derivative of f is just going to be e to the x. Doesn't matter what degree of derivative it is, just going to be that. So then when we think about our next term, it would be the first derivative at 0, and the first derivative at 0 would just be 1. So we're going to put plus 1x, technically over 1 factorial, but in the end that's just going to be plus x. Then for the next term, once again, we're looking for that, I guess it'd be the second derivative now at 0, and again, it's just 1. It's going to be 1x squared over 2 factorial. And then lastly, you're starting to maybe see the pattern develop here. It's going to be 1x cubed over 3 factorial. And at this point, you got the first four terms. So it turns out it's third degree. So if you wanted to go back and put p sub 3 of x, that's fine. If you didn't go back and do it, that's not the end of the world either. But that would be the first four terms of the Taylor polynomial at 0 for e to the x. It did also ask for the general term, and so I'm going to put plus dot 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 plus, and I'm going to try to get this general term in there. Where you start this off is totally up to you. It just needs to just be logical with the pattern. Did anybody have a suggestion on what nth term you would throw there? Did you see a pattern? What do you see?
E to the x times x to the n over n factorial.
Okay, what do you guys think about that? So what I should be able to do is like maybe a mental check here. I should be able to take that and I should be able to put it into an appropriately numbered sigma, right? And it should generate the terms in the series. So if I was going to put that into a sigma, check this out. Sigma from n equals what to what? Where would you start this one out? Lenny, this has to do with you too, perhaps, I don't know. You say 0?
Yes.
Okay, so from n equals 0 to, I presume, infinity. Okay. So e to the x, x to the n over n factorial. So if I started this off at 0, wouldn't I get x to the 0, which is 1, and 0 factorial, 1. Wouldn't you be left with like e to the x times 1? The first term is supposed to be 1. He's got an extra part here hanging on.
Minus
Could you
e to the x.
do e to the Could you do e to the c?
You could do e to the n, I suppose, but then I think that would mess up the other ones too. Anybody have a solution to this? Caroline?
I'm just confused because in the formula it says like f to the n of c. So like if you're using c equals 0, then wouldn't it just be f to the n of 0, which is always 1?
In this case, yeah, that's what I had. If you look at all my nth derivatives evaluated.
For the general one. Like instead of e to the x.
Right, okay. We're not. So when we write the general term, like I'm not as concerned with like where the numbers came from. I'm more concerned with what the pattern of the numbers is. So I agree with you that like the coefficient is going to be like the nth derivative of f at 0, right? You know, the appropriate degree. In each case, it's a 1, right?
Yeah.
So,
Because you plugged in 0 for the x minus c to the n, because it's only x to the n.
Okay, slow down. I plugged 0 in for what?
So, like, in this general equation,
Uh-huh.
I plugged in 0, because it goes times x minus c to the n.
So C was 0.
So c was 0, so it's just x to the n.
You could have e to
So I
the
get-
c. Okay, so e to the
I
zero.
Yeah.
get that.
So it sounds like we totally agree on this.
I'm just confused, like, it goes f, and then, but the first part is f to the n of c. So wouldn't it
And
be
that's
f
what-
to the n of 0?
E to the 0 goes.
Yeah, which is in every case on this one, every single time we do that, it's 1. I'm not saying that this is right.
Oh, so would,
I just asked for your thoughts. I was like, what do you guys think about this? What are your thoughts?
Get rid of the E.
Get rid of the e to the x. Yes, Lenny's right. Get rid of the e to the x.
okay, so
Yeah. So, yeah, I hope I didn't make that too unclear. I would just said, Lenny threw it up there and I was like, what are your thoughts? I would definitely was not saying this is 100% correct, because it wasn't. The e to the x needed to go. Because if you look at this, if you did do the sigma, if you get rid of the e to the x, if you do the sigma from 0 to infinity, you get 1 plus x squared over 2 factorial plus x cubed over 3 factorial, dot, dot, dot. It fits. Yeah. Okay, are we good?
it's 1 because,
It's a 1 because, I mean, this is going to sound really profound. It's a 1 because it's a 1.
yeah.
Because the nth derivative of f is always going to be a 1 for this one.
Okay, thank you.
I know. You guys get it. Other people would be like, what? That's dumb. Why would you say that? But okay. Any follow-ups? So to be clear, this is all correct now. That's the correct nth term. Okay. The next one I am super duper excited about. I'm really excited about the follow-up question with it. So let's check it out. It says, this one's not going to be as easy with the derivatives, because you can see f of x is 1 over 1 minus x. So it says find the first 4 non-zero terms and the general term, and I need to make the same little correction here. The Taylor polynomial at c equals 0 for that f of x equals 1 over 1 minus x. So a little harder derivatives, might take you another couple of minutes to do this one, but same idea, and then we'll try to address those questions on the right. So if you do get done and you're thinking, you know, I'm done, I feel good about this, maybe start to think about those questions. And I'll be curious to hear your observations. So feel free to keep working. I'll just write the derivatives up here.
Yeah, so it'd be positive, positive 1, positive.
Negative
0, which is 0.
The trick on these derivatives is the chain rule, right? Like, don't you have to multiply by a -1 every time because the derivative of the inside is -1?
Oh shoot, I didn't do that.
It's hard. It's easy to miss that. Yeah, McKenna.
Stupid, but why would the derivative be ln?
The integral's ln, perhaps,
Yeah,
right?
that's what I was
It's easy. It's easy to go there. Yeah. Yep.
That was so stupid.
Look at this. So for our polynomial, The first term is just going to be f of 0. And so f of 0 would just be 1 over 1 minus 0. So did you all get 1? Okay, so p of x starts off with 1. And then for the second term, we need to use the first derivative. And so the coefficient is going to be f prime of 0. So did you guys see maybe that the negative times the negative just ends up being a positive? So it ends up being 1 minus 0, which is 1 to the negative 2 is just 1 again. That make sense? Okay. So it would be 1x to the first over 1 factorial. Of course, that's just a complicated way of saying x. And so you might start to think, hey, this is just like e to the x. When you get to the next couple of terms, you can see that they're a little bit different. So the next term, again, I've got a negative 2 times a negative 1. That's just going to be a 2. Then when I plug in the 0 to find f double prime of 0, I get 1 minus 0 is 1, to the negative 3 is 1. It just ends up being 2, doesn't it? So it would be 2x squared over 2 factorial. You can see that there's potential cancellation coming up, right? So then lastly, when I look at this last derivative, again, I get this negative times a negative routine. And if you guys picked up on the fact that 1 minus 0 to the whatever is still just going to be 1. And so it's going to be 6 times 1. So my coefficient is 6. And then it's x cubed over 3 factorial. I think it's nice to see a pattern here by doing some cancellation. So let's do that. So I'm going to say p of x is equal to 1 plus x. 2 over 2 factorial is just 1, so it'd just be plus x squared. And look at that. 3 factorial is 6. 6 over 6 is 1. So you get plus x cubed. And if you did a couple of other terms mentally, I mean, the derivatives obviously are starting to get kind of large. But if you think about this, wouldn't the fourth derivative basically just be negative 4 times negative 6? And then the one after that would be 5 times 24, 6 times 120. It's almost like a factorial building pattern, isn't it? And so each time the whole factorial is just going to be canceled off. So I think, if you wanted to, you could continue this pattern on. It doesn't say you have to, but you could write x to the fourth plus x to the fifth plus ... What would you guys think for the nth term on this one?
X to the n.
Just x to the n, yep. So sigma going from 0 to infinity, we would write x to the n. So that would fit just fine. Okay, interesting pattern. Any thoughts on those questions? Do you recognize this function and series pattern? We'll start off with that one. So the truth is, I'll put it like this. This pattern is definitely rattling around in your brain somewhere because you have absolutely seen this before. Not quite in this context or this form, but you've definitely seen it.
You did it at the beginning of the unit.
Yes.
For the n series.
It is at the beginning of the unit. I'm not sure what you mean by n series.
They're like solving for the n, for the general term.
Sure, yeah. So we did the general term stuff. That's at the very beginning of the unit. The thing I'm thinking about is more along the lines at the start of the time when we started doing convergence, divergence stuff back in like 9.2 or 9.3. There's something back in there that this connects directly to. Why don't I give you a small hint? There's no rule against this. All I did was make all the x's r's. And what did you say, Blake?
Geometric series.
Is it a geometric series? What do you guys think? What's the
R.
pattern for a geometric series? Like, it's kind of the general pattern.
Combination.
I don't know what you mean by combination.
Numeric.
Oh, ratio. Common ratio. Okay, yes. And the common ratio is always what kind of thing?
R.
Let's keep going. R is always a number. Yeah, like a 3 or a 1/3 or a 2/5 or something. And the exponent is always the variable. Yeah, so when you look at this r to the n, can you start to see this taking shape? Okay, so p of x is equal to 1 plus x squared plus x cubed, blah, blah, blah. So like if I wanted to find, say, p of 2, wouldn't that just be 1 plus 2 squared plus 2 cubed plus 2 to the fourth? If I wanted to find p of 1/2, it would be 1 plus 1/2 plus 1/2 squared plus 1/2 cubed, dot, dot, dot. Does that make sense? So if I found p of 2, couldn't you say that the common ratio is 2?
Yeah.
If I found p of 1/2, the common ratio would be 1/2. So this actually is the geometric series, and there's a deeper connection. And to see that deeper connection, let's try to answer this question. This polynomial, this p of x equals 1 plus x squared, dot, dot, dot. This polynomial only converges to a real number if the input is between -1 and 1. Why do you think that is?
Because if the input was 1, then it would just keep adding itself over and over and over again.
And if x was bigger than 1,
It'd be adding a bigger.
yeah, it'd be getting bigger even faster because
Just less than 1, it'd be smaller each time.
that's right. Because x is really what?
Common ratio.
It's really the common ratio. You're right. Now there's one other deeper connection here, and I'm going to circle it in a lovely green color. And I'll specify that right there. Where have you seen that before?
No, not mine.
Sorry?
No, never mind.
It's not in the same form that you saw it before, but it is the same thing. Remember, it's associated with the geometric series. In fact, let me do this. What if I said 1 over 1 minus x equals 1 plus x squared plus x cubed?
That's what it converges to.
Say again?
That's what it converges to, right?
Yes. Isn't this the geometric sum?
A over x.
So we saw this a long time ago. Let me give myself a little room here. We saw sigma from n equals 0, say, to infinity of r to the n. We said that this converges if r is a fraction, essentially. We said it converges to a over 1 minus r. So think about how that a over 1 minus r connects. Isn't the first term in our series 1? And the common ratio is x. And so what this basically is, this is essentially a proof that the geometric series converges to a over 1 minus r. So that the formula that you learned in pre-calc, your teacher's like, hey, here's how you add up all these things. Didn't you basically have to say, okay, didn't you have to sort of accept that because the book said it, the teacher said it, must be true? This is actually a proof for it, right? You have the geometric series, you can show that it converges to 1 over 1 minus x. As long as x is between -1 and 1, you'll get a converging series towards an actual sum. And this is that proof, okay? So I'm trying to make connections back, all the way back to what we've been doing to see that there are connections. I guess that's an important thing, right? Okay, do you guys have any questions at all? Okay. No questions? All right, I'm glad you're not leaving, because we're going to look at perhaps the scariest looking thing of the year. It looks scary, but I will say that its bark is worse than its bite. Are you prepared to be scared? Oh.
There's four different variables in there.
Even the word Lagrange,
1, 2,
scary. Very, very scary. Okay, so I'd like to try to summarize for you guys all of this stuff right here. Listen up. We found all these polynomials. These polynomials are supposed to be representatives of these transcendental functions. And we've done a lot with this. We did a lot of work on the calculator. And remember how we said, essentially, if you've got a polynomial, and let's say it's got like 10 terms or 20 terms, that's simply a representation of the transcendental function. The question of how good of a representation of it is a valid question. And but the idea is that if you have a finite number of terms, you are going to be off. Right? There's going to be an error. It's not going to be a perfect representation. And since we can't write an infinite number of terms, just by their very nature, these are always going to have some kind of an error associated with them. We've already looked at an error, right? Remember we looked at the alternating series error bound? And we said that if you've got a converging alternating series, then the error is bounded by what?
The next term.
Yeah, the next one, right? The first one that you neglected, that's for an converging alternating series. So I've said this a couple of times leading up to this. The question is like, great, that's awesome, but what if the series is not alternating? What could we do? Because that alternating series error bound is very specific for alternating series. So the question is, what if it's just a bunch of pluses, or what if it's like random plus, minus, plus, minus? I mean, like no pattern really. What do you do with that? So the answer to that question is this Lagrange error bound. Okay? You're going to be tempted to think that this is exactly the same as the alternating series error bound, and in some cases it is, and in other cases it's not. So we're going to try to be as precise as we can with all of this. This guy, Brooke Taylor, that I mentioned before, he's known for coming up with what's called Taylor's theorem, and Taylor's theorem is essentially this, that if you've got some function f, then that function can be represented by this. And this part right here, doesn't this look really familiar to you? Isn't that what we've been doing for the last day and a half?
Yep.
Doing a Taylor polynomial? And so he says, you can write this polynomial to represent any function, but there's always going to be this error on the end of it, right? So whenever you stop writing terms, whether you do 10 or 20 or just 2 or whatever, whenever you stop, there's going to be a specific error bound associated with that number of terms. So we've said it before, like if you decided to write 20 terms in a series, then the error will probably be less than if you only wrote 10 terms, right? So on and so forth. So he's just saying that there is an error associated with the number of terms that you choose to write. And he quantifies that error with this right here. I know that looks pretty scary. We'll talk about what all this stuff means in a second. The proof of this is a little bit beyond the scope of our class. It would be an analysis class. I actually showed this a couple of times. It literally took 1 hour to show the proof for this. At this stage of the game, I'm not really willing to spend a whole hour doing that. And it took the whole board. It was the coolest looking thing ever. And at the end, I feel like some of the class was like, cool, I'm with you. Others were like, what? But 100% of them didn't really need it at this stage. And so I thought, yeah, maybe we'll hold off on that for the moment. Yeah, you're gonna have to take your book's word for it. You have to take my word for it a little bit. I mean, that's just the honest truth. You know what? If you're really curious, over Christmas, somebody showed me there's a pretty cool Khan Academy video. Probably take you about a half hour to watch it or so. Maybe you can't. Maybe you should do it for yourself. It's I don't know, or take an analysis class and like delve into it yourself. You can. Anyways, let's break this down. Let's try to look for some familiar stuff. So I would say I'm hoping that this right here looks pretty familiar to you. Isn't that kind of the standard error form? Like actual value minus the polynomial's value tells you how far you are off. And we equate that with this error, this r sub n. So we're saying the difference between the real sum and our approximation, that's the error. And here's where we get into this Lagrange error bound. This is less than or equal to the absolute value of x minus c to the n plus 1 over n plus 1 factorial times max. Oh my gosh, and there's a z in there now. What? Let's break this down. There are two parts of this that are very formulaic, that require very little higher level thinking. I want to highlight those for you. These two are very formulaic. So let's talk about what those different pieces are. C is our centering number, right? So if you've got a polynomial centered at 2, C is 2. If you've got a polynomial centered at 0, C is 0. So C is the same thing that it's meant this whole time. X is the number that you are plugging in to generate your approximation. So we've done these before. So if it said, we did one earlier where it said, find the Taylor polynomial for such and such, then estimate f of 1 or something like that. So in that case, x would be 1, but x is the number that we are using to evaluate the series and approximate the function. N is simply the degree to which the degree of the polynomial that you used. I mean, that's been pretty standard material up to this point. And so I would say, like these two right here, these two pieces are very just cut and dried. You plug in the x, the c, and the n, and there's no debating about what those are. The thing on the right is a little bit fuzzy. The thing on the right is a little bit tough because it says we want to know the max value of the n plus 1th derivative of z. We've got x's, we've got c's, but where does the z come from? Here's what z is. Z is some number on the interval from x to c. You think about the c, you think about the x. Z is going to be some number in between there. And sometimes it's going to be super easy to figure out what z should be. Sometimes it's going to be kind of hard, and we're going to have to go with our best estimate. And I know for a mathematician to hear the words, just use your best estimate, it's a little scary. It's going to be basically the best thing you can do based on what you're given. Sometimes you're going to be given enough information to like pin it down and be like, yep, z should definitely be this. Other times you're going to be like, well, it's going to be about that. Other times you're going to be like, well, you'll see in a little bit, there's going to be like a graph, and you're like, well, based on the graph, this is what I got to go with. There's going to be some fuzziness to the logic on some of these, so you just want to be prepared for that. Okay, so what I thought I would do is do one of these with you and just kind of like try to show you the ropes a little bit, show you how you handle this, and show you an example of what this might look like. And then we'll have time, I think, probably for at least one more. And then maybe might be kind of nice to stretch one of these out through into next Tuesday and just kind of see where we end up. Okay? So I'd say example 1 is a really nice place to start. You already know this because you just figured this out about 20 minutes ago. It says the first 4 terms of the Maclaurin polynomial for e to the x is given by p of x. And you can see that that's the exact same thing that we figured out. 1 plus x squared over 2 factorial plus x cubed over 3 factorial. So the first thing you want to maybe notice here, knowing where we're headed, did you notice that this is not an alternating series? It's just plus, 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 plus. And so if we were going to go on to try to find some error bound and we use the alternating series error bound, we would just be wrong because it's not an alternating series. So it says use Taylor's theorem to approximate e to the point 1 by finding the polynomial at point 1. And then we're going to deal with the error. So let's go ahead and do this. I'm going to say e to the 0.1 is approximately equal to p of 0.1. And of course, this is the beautiful thing about a polynomial. All I got to do is plug in a 0.1 in for each of the x's. And I would say a calculator would for sure be active here. So if you would, get on your calculator and let's actually figure this number out. 0.1, or like 1 plus 0.1 plus 0.1 squared over 2 factorial, so on and so forth. Take just a minute. Let's figure out what this number is. Well, let's go to 3 decimals, kind of the standard, 3 or more, I guess. We'll see. See what this answer ends up being. Then we'll try to deal with the error. What'd you get?
1.105.
1.105? It's definitely got to be 1 or bigger, doesn't it? Yeah. So that certainly makes sense. We in agreement? 1.105. Solid? Okay. So that's our approximation, and if you wanted to, you could figure out what e to the point 1 is and maybe see that there is some degree of error here. Or maybe it's close enough, like that one we did where you can't actually see the error on the calculator. I don't really know. So here's what we got to do. It says, we found this. Now it says, and show that the maximum error for this approximation is less than that number. And that's a pretty tiny number, but we want to show that our error is less than that. So we're basically setting like an acceptable level of error for whatever our purposes might be. We're setting that level of error. So here's what I'm going to do. I got to recognize that this is not an alternating series, so I got to use the Lagrange error bound to do this. So I'm going to say something like this. Maybe I'll start over here, and I'll say e to the 0.1 minus p sub, what was it, 3? Yeah, it's third degree, so it'd be p sub 3 of 0.1. That's my error, right, because it's the actual value minus my approximation. So this is going to tell me how far off I am. This is going to be bounded by, so we're going to say that that error is less than or equal to. So like I said, these first 2 elements are totally canned. Like the numbers just go where they go. So for example, what is x? 0.1. It's the number I plugged in to evaluate my polynomial. So 0.1 minus, what's c? 0, because it's a Maclaurin polynomial. You can see the centering value for the polynomial is 0. So 0.1 minus 0, and it's going to be to the n plus 1. So what is my n? 3, right? I went to degree 3 with my polynomial, so n plus 1 would be 4. And then n plus 1 factorial, well, that would just be the same n plus 1 as we had up there for the exponent, so it would be 4 factorial. And at this point, I've got all of the easy stuff out of the way. And I don't think this next part is that bad either. So this next part, the max value of the n plus 1th derivative. So let's establish this. What's the n plus 1th derivative? So specifically for this scenario, it would be the 4th, right? So the 4th derivative. And I've set you up for success here, right? Because what's the 4th, 5th, 6th, 7th, 8th, or 10th derivative? E to the x, right? Okay, so your 4th derivative, I'll just write this up here just as a little note. My 4th derivative is e to the x. So what I've got to do, maybe I'll tell you what, this might make it easier for you. You all know what this looks like because you've done this a zillion times. Will you guys graph e to the x on your calculator real quick? But set your window to be our interval from 0 to 0.1. Set your interval just specifically on that so we can focus on that part. So when you graph this on this window, you guys get something like that? E to the x? Like if you literally graph it from 0 to 0.1. Does your window look something like that?
I messed up my calculator.
Okay. Does that make sense? Okay. So this right here, use a little different color to emphasize this, I guess. This is c, this is x. So this number z is some number between, on this interval, such that it's going to produce the maximum value of this 4th derivative. So as I look at this graph, this is a graph of my 4th derivative, right, which is e to the x. So what value on that interval would make this derivative the biggest it could possibly be?
That would be 0.1.
0.1, right? So you look over here, we know the value right there is 1. And over here, it's going to be something a little bit bigger than that, right? We can see that it's increasing. So here is where there could be some fuzziness to the logic. If you've got a calculator, don't you know exactly what e to the 0.1 is, or at least a good approximation of it? You could just say, yeah, e to the 0.1, that's going to be the max value of the 4th derivative on this interval, right? If, however, maybe you didn't have a calculator, you didn't have the ability to figure out exactly what it is, this might be a place where you'd have to guess a little bit, and hopefully it works out. So without the calculator, maybe you've already figured this number out, without the calculator, what would you say? Like, what would be some logical guess you could throw out there for this value over here, such that you know for sure that your guess is not too low? What might you guess? Think of a nice, easy-to-use number. 2, right? Aren't you pretty confident that e to the 0.1 is something less than 2? So if you didn't have a calculator, maybe you'd use a 2 here. Like you'd use a logical, easy number to guess. But we're presupposing that we do have the calculator, so let's go ahead and do that. Okay, so e to the 0.1 would be this max value. Is this making sense? Max value of the 4th derivative. It's the highest point. So I'd come back over here and say, you know what? Looking at the graph, understanding how this works, I'm going to say the max value of that 4th derivative is e to the 0.1, some crazy decimal, right? So at this point, what you'd do is you'd evaluate this. You'd go 0.1 to the 4th, divided by 4 factorial, and then take that times e to the 0.1. Okay? Anybody done that yet? If you haven't, go ahead. Let's check it out. Any numbers yet? Yeah, for the whole thing. So it'd be 0.1 to the 4th over 24.
4.605 times 10 to the negative 6.
Okay. 4.605 times 10 to the negative 6th. So remember the goal here was to show that our error is less than 5 times 10 to the negative 6th? And can you see that just by barely, our error is less than that, right? So we could say this is less than this 5 times 10 to the negative 6th. So I would say that this number 5 times 10 to the negative 6 is an arbitrary number that somebody said, hey, this would be, if our error is less than this, we're good. So this number really has to be shaped by the tools that you have. I knew that you had the calculator, so it'd be pretty easy to figure out what that max value of the fourth derivative would be. So I set a value that you could attain for sure. If you didn't have the calculator, I probably would have had to set the error to be maybe a little more generous, right? Because it would have been hard to pin down what e to the 0.1 actually is. Okay. So let me just review this really quick. Would you guys agree that this part here and this part here are really just like formulaic? Plug, 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 right? And you also agree that this, maybe at this stage, you might not know quite how much thought it would take. Do you see how this might take a little more thought? Okay. Let's see where we're at here. I know we got another one coming up. Let's see what this looks like. I think, yeah. I don't know. Let's at least do A. If we do A, we'll be setting ourselves up good. We might not be able to talk too much about B, but let's go ahead and do A. This is a good practice to do another Taylor construction about x equals 0. So I don't know. See what you can do. We just got a couple of minutes here. See if you can do this, and I'll do the same thing. Do you guys remember in the chain rule on all these derivatives? Be careful with that. You guys get a bunch of root 2 over 2s for your coefficients?
Yeah.
Okay. This will probably be where we finish here. I am coming up with a Taylor polynomial of, I got f of 0 is root 2 over 2. So it'd be root 2 over 2 plus, I got f prime of 0 is 5 root 2 over 2. So 5 root 2 over 2 x to the first over 1 factorial. And then let's see here, f double prime of 0. Now we're into negative, so it'd be negative 25 root 2 over 2 times x squared over 2 factorial. I guess I got to do a little erasing here. So my third derivative at 0 would be minus 125 root 2 over 2 x cubed over 3 factorial. We in agreement on that? Okay. So then what we'll do with that next time is we'll get back into this Lagrange error bound. I thought that'd be a good place to finish with constructing a series. I don't think we'll do too much more of that here for the next week or so. So anyways, we will pick this back up. For those that are going to be gone on Tuesday, we'll obviously continue on. Monday we will not. Anyways, hope you have a great weekend and good trips and retreats and whatever. See you guys next week.